Hey everyone, my name is Imal and welcome to a series of videos where we will be implementing linear regression from scratch. This is the third video of the series of videos on linear regression from scratch. Let's go right into it. Okay, we need to essentially minimize j with respect to theta in this equation. J of theta is equal to norm of y minus x theta whole square. This is a continuous, convex and quadratic function, and therefore will have a global minima. When I say continuous, convex and quadratic function, I mean it's a function that looks somewhat like this. It is continuous everywhere. It is convex because it has a bulge towards the end. It looks like a bowl, and quadratic because it has a quadratic power. And therefore it will have a global minima. And if you look at the figure here, the global minima is clearly evident. And that is what we want to find. We want to find the point where we can minimize this equation. So we find the minimum by finding that one place where gradient is 0 in all directions. How do we find the minima of this function or this equation? Is by finding that one place where gradient is 0. So gradient is a concept in calculus. We will not get into what gradient is, what differentiation is, all of that. But if you want a refresher, maybe you can just go and search gradients in calculus and you will get what happens. We will see some aspects of differentiation here, but we are not going to go into much detail. Now let's get started. How does one take gradient of squared norm of a vector? J of theta is given by norm of y minus x theta the whole square. Can I write this as a product, or y minus x theta times itself? And in linear algebra, this is how I would write it. So if you look at the first equation, gradient of j is equal to gradient of y minus x theta transpose times y minus x theta. Going further, now we will multiply these two expressions individually. So gradient of j is gradient of y transpose y minus x theta transpose y minus y transpose x theta minus theta transpose times x transpose x times theta. Now y transpose y is a constant with respect to theta. So this term disappears. And the next two terms are equal because transpose of a scalar j is scalar, right? So if you have a scalar and if you take transpose, it is scalar. And the final term has quadratic form. And the general rule is x transpose times ax is equal to a transpose x plus ax. But because product of a matrix with itself is always symmetric, we can write x transpose ax is equal to 2ax. And these results will help us simplify this above equation further. Okay? Now, if you're getting confused, what I'm essentially saying is y transpose y is a constant with respect to theta. So this term does not matter, and differentiation of a constant is 0, right? Gradient is essentially taking a differentiation here. And then you see the next two terms, and they are both equal, right? If you look at them, they are both equal because transpose of scalar j is scalar. So both of them can be said that they are equal. And eventually the third term has a quadratic form, and if you look at that, it follows the general rule x transpose ax is equal to a transpose x plus ax. Here x transpose is theta transpose, a is x transpose x, and x is theta. So that will be broken into 2 times ax, which is 2 times x transpose x times theta, which we will see further. So, like we discussed earlier, we can now write the gradient as gradient of j is minus 2 x transpose y plus 2 x transpose x theta. This is coming from the previous equation, just simplifying the previous equation. And at the minimum, we've discussed this earlier, at the minimum, the gradient in all directions is 0. Therefore, for the minimum case, we have 0 equal to minus 2x transpose y plus 2x transpose x theta, because we said at minimum point, the gradient is 0. And now we are saying we want to find that point. So 0 is equal to minus 2x transpose y plus 2x transpose x theta. Doing some reshuffling here, 2x transpose x theta is equal to 2x transpose y. X transpose x theta is equal to x transpose y. And this is the so-called normal equation. This is not something that we put out initially, but this is the normal equation that will allow us to find theta. This is a very important result that we have reached right from where we started. And this is important because this equation is in terms of only x and y. If you look at this equation, you will see that there is x, theta, and y. And we want to find theta, right? We've almost reached the end. We've almost reached the end. We have a way to find theta now. But how are we going to solve this? How are we actually going to find theta? We can find theta by substituting and eventually substituting x and y and finding theta. But there's an even simpler way, and that is, since we already know x and y, we can just plug in x and y to solve for theta. But there's a faster and more numerically stable way using linear algebra techniques, and this is what we will discuss in the next few slides. And this is called QR decomposition. And in linear algebra, a matrix A can be decomposed or factorized as A is equal to QR, where Q is an orthogonal matrix and R is an upper triangular matrix. Okay, so if you have a matrix A, you can represent that as a product of two matrices. This is very similar to the factorization we learn in our high school, in the middle school or high school, right? We are trying to find the factors of this matrix. Now, Q is an orthogonal matrix. What it means is that its inverse exists. Or if you multiply Q with its transpose or inverse, you would get an identity matrix. And R is an upper triangular matrix. We will see what an upper triangular matrix is as we go. But why do we use this technique? Because it's easier for computation. So if you have an equation like ax equal to b, where you would like to find x, then what you could do is compute a is equal to qr first, and then write the problem as rx is equal to q inverse b, which is very easy to solve given q is orthogonal. Therefore, q inverse is equal to q transpose. And R is an upper triangular matrix, which helps to solve the equation using a technique called back substitution. Consider the following matrix. If you see this matrix, like I said, we will look into the upper triangular matrix in the future. The matrix on the left with elements 4 to 6, 0, 2, 2, 0, 0, 8 is an upper triangular matrix where all the elements below the diagonal are zeros. And essentially what is happening here is you see this matrix R times X is equal to Q inverse B. And using this, you are trying to find X. Okay? And how do we do this? On multiplying the matrices, we will get 4 times x1 plus 2 times x2 plus 6 times x3 is equal to 4, 2 times x2 plus 2 times x3 is equal to 4, 8 x3 is equal to 16. We solve the third equation first, and we get x3 is equal to 2. Very simple. And this is why it is advantageous to have R as an upper triangular matrix. All right? And we basically, after we find x3, we substitute the value of x2 in the second equation. We get x2 equal to 2, x2 equal to 0. Similarly, we can substitute x2 and x3 to get x1 is equal to minus 2. Now we have x1, x2, and x3. Now, we're coming to the linear regression part of what we wanted to solve. We are almost at the end. Recall that we wanted to solve the following equation. X transpose times x theta is equal to x transpose y. And we discussed earlier that we could decompose a matrix A is equal to QR using QR decomposition. Now in this case, let's now say that QR is a QR decomposition of X. In that case, we will get Q transpose times R transpose into QR into theta is equal to QR transpose times Y. Essentially what we're doing is replacing X with QR, because we used the value of X to find Q and R, right? So R transpose times Q transpose Q R theta is equal to R transpose Q transpose Y. Since Q is orthogonal, Q transpose Q is equal to I, identity matrix. Therefore, we will get R transpose R theta is equal to R transpose Q transpose Y. R theta is equal to Q transpose Y. We already have the values of R, Q, and not theta, it should be Y. Sorry, R, Q, and Y. We plug it in the above equation to find theta. Yes, that's it. We've found theta. And with this, we come to an end. That's it, folks. We've successfully managed to find the coefficients theta given a certain x, y using statistical deductions and linear algebra.